Good morning, everyone. This is the High Performance Computing Unit, CITS 3402. My name is Amitava, and I am the lecturer and the tutor and the coordinator for this unit. So first, I'll give you an overview of the administration of the unit, and then we'll proceed to some of the technical aspects that we'll cover in this first lecture. As you can see, you have a unit page which is accessible from the school homepage, and I guess all of you know how to access the unit page. Now you can see the lecture and lab times there. There are 2 lab sessions for this unit, and also I'll soon keep a link to the lecture recording from the unit page. Unfortunately, the first lecture was not recorded because there was some problem with the recording system, but from now onwards, from second lecture onwards, there will be lecture recordings and it will be available from the unit page. In addition to the lecture recordings, I'll also record short videos like this one using my own setup in my office, and I will connect these lectures from the unit page through a Facebook page and also a YouTube channel. However, it's a bit awkward for me in the beginning to record lectures like this, and I hope I'll soon get better, and better in the sense of using the pen. As you can see, I have some difficulty with the use of the pen, but I'll improve, I'm sure. You can also find all the resources for this unit from the unit page. Resources in the sense that we have some recommended textbooks and also lecture slides from other sources. In particular, in the first part of this unit, we'll use some lecture slides from the openmp.org site. First, I'll start with the need for high performance computing. Why do we need high performance computing, and why there is a need for a unit for high performance computing? All of you know that today's computers are very fast. There is no doubt about it, and you are all familiar with the very fast speed of computers. For example, when you run your programs for most other units, even if your programs are quite large, they run almost instantaneously. There is no doubt. However, we'll see soon that there are programs in this world which are very expensive in terms of running time, and they require a lot of computing power and a long time to run. Moreover, people are trying to solve larger and larger problems as computers are becoming faster and faster. Some programs never even complete their execution. One of the good examples is the weather simulation or weather forecasting programs that all of you are familiar with. Perhaps you listen to the weather forecast in the evening news programs in the TV channels, and those programs are so complex and so time consuming that most of the time what you hear in the news channel is just the current forecast. That is, whatever the program outputs at present, and the simulation continues for future forecasting. So one of the things which we can admit or we can accept is that even though the speed of hardware is improving, computers are very, fast, but hardware is never able to keep up with the demands of faster execution of programs. And hence, we have to look at different ways of improving the performance of our programs. To understand high performance computing further, we have to look at the evolution of processors or understand how processors have evolved over the years. Now, what is a processor? A processor is basically an electronic chip, and all of your computers that you use in your day-to-day activities, like your desktop computer and your laptop, mobile phone, etc., they are all equipped with a processor. And processors have become more and more powerful over the decades. In fact, there is a well-known law or hypothesis, if you like, called Moore's law, which says that the processor speed has improved or increased in power. Almost the processing power has doubled every 18 months. Gordon Moore, the founder of Intel Corporation, proposed this law in 1965 or 1966, and it has held true since then, almost until 2009. So how does a processor become more powerful? Processors become powerful by packing more and more electronic circuits within a small chip area. Today's microprocessors can pack tens or hundreds of millions of transistors in the single chip. However, the problem with this approach is that as you pack more and more circuits within a single chip within a small area, these electronic circuits dissipate power during their operations. And electronic circuits are made of semiconductor devices. Semiconductor devices are very prone to fluctuation in their performance depending on their temperature, the ambient temperature. The reason is quite simple. If you know a little bit about computers, you know that computers internally act with the help of binary arithmetic, that is zeros and ones. The 0 is represented by a lower voltage and the 1 is represented by a higher voltage. Now, if there are fluctuations in the temperature, these voltage thresholds, for example, the 0 could be 0 volts and the 1 could be 1 volt, or 5 volts, the voltage thresholds kind of mix up. That is the inherent property of semiconductor devices. So they should be kept apart for correct operation of the circuits. And hence, high temperature is not a good idea or good approach to have for reliable performance of these electronic circuits. And hence, cooling is necessary. However, there are limits to cooling, as you might have noticed that every processor today comes with its own fan, etc. But there is a limit or threshold beyond which it can't be cooled effectively if you pack more and more circuit elements. And also there is another problem that today's computers or circuit elements are so small that they are almost reaching the physical limits. For example, today's transistors in a microprocessor can occupy a few tens or hundreds of atoms, for example. And this is something which is going to the limit because you cannot really pack more than that, in the sense that you cannot have a transistor which are or transistors which are smaller than a few atoms. So keeping all this in mind, what has happened over the years, and particularly around the time of 2009 and 2010, that semiconductor companies or companies like Intel, they realized that packing more and more circuit elements requires tremendous amount of investment in terms of dollar investment for manufacturing very sophisticated machineries. However, the power problem is beating them in the sense that it is very hard to cool these processors. So they have gone towards the direction where instead of a single powerful processor, they have now multi-core processors. That is, multiple less powerful processors on the single core or single die. I shouldn't have used core, but rather single die. Now, what does that mean? That means that instead of a very powerful single processor, you have multiple less powerful processors, and you have to make use of those processors in the sense that you have to use them for executing your programs faster and faster. Now, this is highly non-trivial because earlier you used to write programs with a sequential execution in mind. Now you have to write programs which can be decomposed into multiple parts for running on multiple cores. And of course, this whole unit is based on that idea, how to decompose big problems into smaller problems and execute them in parallel. There are two related issues regarding this, concurrency and parallelism, which we'll briefly look at now and we'll go back later in more details. Concurrency is the simultaneous execution of multiple tasks. So, for example, when you are using your laptop, you could be browsing the internet, you could be listening to music through an MP3 player, and you could be as well coding in C and compiling those C programs and running them. Now here, multiple tasks are getting executed simultaneously. However, simultaneous may mean two things here. One is logical simultaneity, that is, the computer or the processor is actually executing your tasks like your MP3 player, your internet browser, and your C programs one after another in quick succession. And human response time is much slower compared to the computer's power. So what we feel as simultaneous is actually execution one after another. So this is called logical concurrency. However, there could be physical concurrency if you have multiple processors in your computer or multiple cores in your computer. And that is called physical because in that case, all of your tasks are getting executed truly simultaneously in parallel, and that is called parallelism or physical concurrency. Now, we will study parallelism in this unit in a more deeper sense. We'll study the breaking up of a task into smaller tasks and solving these smaller tasks simultaneously. So instead of considering the previous scenario where you had several applications that you are running at the same time, here we'll run a single application, but we'll try to break that application into smaller parts and run on multiple cores or multiple machines. Now, of course, these smaller tasks will only give partial results, and we have to combine these partial results to get the final result. Here is a simple example. Suppose you have to add 1,000 numbers. You can either do this on your own or recruit 10 friends, each of whom can add 100 numbers at the same time. And at the end of it, you will have 10 different sums which are not the complete sums, but which are only partial sums. And you can then add these 10 partial sums to get the final sum. Now the whole aim is to complete the task 10 times faster by taking help from 10 different friends. And that is parallelism in the sense of parallelism that we'll study in this unit. So high performance computing is about parallelism. Our aim in this unit is to study parallelism on machines that have multiple processors. There are many such machines starting from your laptop, desktop, mobile phone, PlayStation, Xbox, and even supercomputers. In fact, we have a supercomputer at UWA in the physics building. the Fornax supercomputer. However, in this unit, we'll study two kinds of machines. One is multi-core processors, as I have mentioned before, and the other is cluster of workstations. The cluster of workstations can be viewed as a parallel machine if you combine several of your desktops into a network and can solve problems by breaking them up into smaller problems. So the first one is readily available in your desktop or laptop computers, and the second one is called a distributed memory architecture. The first one is actually called a shared memory architecture because we'll see that the threads that will run on your multi-core machines will share their memory in some sense. We have to understand that later. And a distributed memory architecture is a cluster because here the memory is distributed among the different computers or different desktop machines. So this is the end of this introductory video, and we'll go into more